Okay. Tells me that it's recording, but I can't see any green light for audio and video. Audio, yes. Okay. So some of you know that last week the audio recorded but not the video. So I'm trying to see if we're getting video this week or not. Doesn't look like we are. Okay. My apologies, everyone. I'll just try this so that we can do our best to get a video and audio this week. Okay, so the display is it's slowly opening up here, and it looks like we've got video and audio. So hopefully that's good for people who are listening at home. And please let me know if there's any issues again this week with the quality of what's going on. Now, there we go. Okay, so by the time you finish this second prac that you're working on, you're already halfway through the quantitative pracs for this course. So as I said, that this course will give you an introduction to research methods. It won't make you an expert, unfortunately, at the end of it, but it'll give you the right building blocks to head in that direction. And again, we're trying to take an applied approach. So we want to keep asking, well, how can we use this to solve management and planning problems out there in the field. So this week we're going to look more closely at inferential stats. So we've already come across some of this in the pracs, which is great, and so we'll build on that and prepare for the third prac, and then you'll be 3/4 of the way through. So the idea of today is that we make sure that these common terms are understood in terms of inferential statistics. We've already talked about when to choose between a non-parametric or a t-test, and we're going to look a bit more closely at t-tests. Again, I'll just be giving you an overview and then you'll get to jump into it in the prac, and we'll give you a bit more information as you go along about t-tests and different types of t-tests. We're also, in preparation for the prac, going to look at tests for correlation between two variables. So we'll set you up for the prac group for next week in terms of those sorts of questions, and also how to understand what's going on there in terms of correlation and the sort of stats that SPSS will generate. Now, some of this we will also touch on in the middle, evaluation research, because the prac this week will be looking at a type of evaluation research, a project that was done in Alaska on urban moose. And so somebody had the fun of running around, probably in the snow, collecting moose poo to crunch the data. You don't have to do that side of it. Sorry if you, it would be kind of fun to be running around in the forest. But these moose were actually partially in the forest and also in urban areas. I'll talk more about that if we have time at the end of this lecture. Otherwise, in the introductions to the pracs, I've also posted a little bit of info in Blackboard on that. Number 7 there, I'm going to post those as slides. They're pretty self-explanatory, but just to explain what this is about is that we're seeing the need for this more and more. As scientists often talk about, well, wouldn't it be great if we made most major decision-making in an evidence-based way? And so there's a few slides there to get you thinking about what would a future society look like, a culture that was based on making decisions on evidence-based decision-making, i.e. evaluating what's going on and then deciding rather than basing it on ideology. Unfortunately, we won't have time to go into depth in the lectures on that, but if you want to discuss with your peers, I encourage you to do that, particularly those of you who've had any dealings with large organisations or even in the workplace. You'll know that as a species we're not quite as rational as we think we are. So it's a real challenge on how do we chart a future that it takes evidence seriously in decision making. Okay, I just wanted to put this up at the start and the end because this is the basis for the practical, for the class, today, is to set you up for, well, it says tutorial, but it's the third practical. So looking at independent samples, t-tests, so comparing two different groups. So understanding what those results are when we do a t-test, so looking at that t-statistic. We're also going to look at correlation, both visually in terms of scatter plots and also in terms of statistical tests and understanding those. Can I have a quick show of hand? Who has done this sort of thing before? T-tests or correlation? Okay, only a couple. Great. Okay, so we're going to do it in 3 parts. First, we'll look at the foundations that are sitting underneath it. There's a few calculations on the slides, but that's just to demonstrate how you could calculate it by hand so that you understand when we're using the software what's going on behind that. Then we'll have a quick break, talk about evaluation research and testing between 2 different groups. Okay. So, in terms of foundations, you've already done a little bit of this. Whenever you've done a statistical test, you're doing inferential stats. But it's important that you understand that what we're actually talking about is sampling, taking a sample from a broader population, and then there's a whole bunch of symbols that you might see coming up in this sort of in statistical reports. These ones over here are talking about the broader population, and then the statistics, we call them parameters. These ones here, statistics, are what we get from our sample. Okay, so whenever we talk about doing a statistical test, we're talking about getting some sort of result from our sample, and then using those results to make some sort of inference about the broader population. Okay, so we need to clarify what the foundations for this are and for the sorts of things that we need to keep in mind as we're doing this work. So we're going to take the sample mean and then say something about, infer something about what that means for the population mean. Same for standard deviation, etc., etc. So there's I'm trying to put the jargon in a slide at the front. You can read through that and check that you understand. The only one I didn't mention there is the sampling error, but we'll come back to that as we go along. But that's to give you a quick overview. Basically, if we took one sample and then we took another sample, the sampling error is talking about the variation between those samples and due to chance, okay, just due to the random sampling of that population. Okay, we'll keep trying to give you examples as we shoot through this. So inferential statistics studies a sample to learn about a population. So for example, residents of a particular town or bandicoots in Queensland, and then the sample is, in the first situation, a survey or interview participants from that town or about that town, and the second one, bandicoots in Queensland, might be a particular sample of bandicoots that we've trapped and then taken measurements on. So descriptive stats, which we've been doing the last couple of shoots, tells us about the sample, but inferential stats allows us to use the sample to understand the population. Okay? Descriptive stats just tells us about the qualities of our sample. Inferential stats allows us to infer something back about the broader population. So obviously in planning and management, where we're dealing with large, even we often don't know the true extent of the population that we might be dealing with. This is very important work around taking a sample that we do understand and then to what extent can we infer something about the bigger picture. So the key to all of that is probability. So when we're inferring back, we need to be able to say something about how probable is the results from our sample accurately reflecting what's going on in the broader population. And you'll know when you go into the workforce as planners or managers that you need to have your business case strong because you'll very rarely be the people calling the shots in an organisation or on a particular project. You know, even on a planning consultancy, you'll be giving that to a client, and you'll need to be able to back this up with good data, whatever you're saying. Yeah, my phone's not on silent either. So inferential stats help to interpret the data and draw inferences about the population from a sample. So, for example, does social housing reduce social inequality? You would probably take a sample of people in social housing and people who aren't in social housing who are in marginalised groups. Does transport-oriented development reduce greenhouse gas emissions? Again, you would want to have some different samples of different types of development and measure their emissions. Does mandatory OHS training reduce workplace accidents? Again, you can take different samples of different workplaces that do have or don't have OHS training. Obviously, we can't survey the entire population for any of these, so that's why we have to take samples. Also, you're never going to have enough money even if you could look at everything. So we've already met the normal distribution. Now we're going to talk about how that provides a foundation for this sort of work in inferential statistics. So it's based on this idea of a central limit theorem, that if we sample enough, if we get enough samples, then eventually we'll get a distribution that is normal, conform to the shape of a normal distribution. There'll be some sort of central tendency and some sort of variability or spread of the data. So, for example, you're measuring 50-gram samples of soil. It's very unlikely that every sample is going to be exactly 50 grams, but if you have enough samples in there, then you'll be able to treat them as if they are all 50 grams, because every sample that you do is going to reduce that variability. But if you look at them very closely, you'll also see a normal variation, as long as your measurements are not skewed in any way, around the 50 gram as your mean. So this is one of the problems with these slides that I realised, is I'm going to use mean in two different ways, okay? So the mean, we're talking about the average in this course, but English, I'll also be saying this means. Okay, so just double check that if English is your second language and it's confusing. So basically, that's why we're so concerned about normal data, because it means we can use an understanding of probability to make these inferences from our sample to the broader population. So we're going to look at an example based on weight. So if we had a population of 1,000 people and we weighed them all, and we had a mean of 100, this seems like a fairly high mean. I mean, I'm getting close to 100 and I shouldn't be. So just say we had a mean of 100 and a standard deviation of 10 kilograms, okay? And if we had enough samples, 1,000 is enough, we're going to get this nice bell shape. And so the question is, if you walked up to one person in that 1,000 and just tapped them on the shoulder, what are they likely to weigh? Are they more likely to weigh 100 kilos or 80 kilos? And you can see visually straight away that they're more likely to weigh 100 kilos. You know, you would know that just by thinking about it. But if we want to get a bit more precise, we could say, well, actually, if you measure it, there's 79 people at the 100 level. So that's 7.9% of our 1,000. And then there's only 10 people down here at 80, and so that's 1%. Okay, so you can start to say something a bit more specific about the likelihood of selecting particular people at particular weights. And you can do that for ranges as well. You could say, well, what's the likelihood that when we tap someone on the shoulder, they weigh between 95 and 107 kilograms? And you'd have to do a bit more maths to do that. Luckily, SPSS does that for us. And so you would basically do the same thing that we did for tapping one person before, but to do it across that range, and you would come up with, you've actually got a 45.2% chance of tapping someone on the shoulder in that range. So what about out near the 80 kilo area again? If we tried to sample 69 to 81 kilograms, I wonder what the chances are of falling within that range. So you could do that, calculate it all from first principles if you had to, and you can see that there's only a 2.5% chance that if we sampled, that our sample mean would be out in that area, in that range, okay? So if you randomly tap someone on the shoulder and asked their weight, you might have a 45.2% chance that they would be within that range, and a 2.5% chance that they would be in that second range. Okay, so hopefully all of that's pretty straightforward. We'll build on that. So just say we take a sample, and before that 1,000 is our broader population, and we're going to say we've got a sample of 60 people, and on average they weigh 74 kilos. Okay? It sits down there like that. And if you say, well, what's the chance of selecting 60 people in that sample in that range? We know from before that it was a chance of 2.5% of selecting one person. So what's the chances of selecting 60 people? It's 2.5 by 2.5 by 2.5 and so on. And so you end up with 0.25 to the power of 60, okay? Which, if you're wondering, is very small, okay? It actually, in a percent, works out at less than 0.01% once you have a sample out there near the tails. So you can see, very unlikely that you would just randomly select that sample without something else going on there. So, again, hopefully, just raise your hand as we go along, but hopefully we're building here. We can then take some of those understandings and then we know about this normal curve, and we can do some nifty things with probability to compare what's going on between samples and populations. So we know that if all our data sits under this curve, then the probability of being under that curve is 1. Everything is under that curve. Okay, the total area under the curve is 1 for this probability distribution. So if we were to have an area X and we knew what X was, the probability of having not X is 1 minus X, so that it adds up to 1. And so what statisticians have done is they've set up a standardised approach to this normal curve, which means that if we can set up a standardised curve, remember whenever you see a Z, where Z score is a standardised score, it means that we can read this Z score here, which is along this axis, and it will tell us what the probability is of sampling to this side of the Z score, okay? So sampling to the left of the Z score. Let's show you. So just say we get a probability, that X that we had before, just say that is negative 0.98. Now this is standardised, which SPSS will do for us. But if you had to read it off a table, you'd go through, there's negative 0.98, and the probability of getting that Z score is 0.1635, okay? And so that normal distribution we just looked at has a mean of 0, standard deviation of 1. And so it's a standardised normal curve, and when we do that, we can then use those tables, we can use that software, we can compare different samples and different distributions and work out their probabilities. And then that means we can check what the probability is, how likely or unlikely it is of getting that sample from the broader bell curve population according to chance. Okay, so let's come back to the one that we looked at before. We know that it's really unlikely that just by chance we're going to select 60 people that have this sample out here and a mean of 74. If we're looking at it on the bell curve, it's right out at the tail out here. Now, you can sift through this to understand it, but this is how it gets standardised. Basically, you take the sample mean, which is, remember our little pyramid here, the sample mean was 74. You divide it by the population mean, which in that case of the broader population was 100, and then you divide it by the standard deviation of the population, okay? Again, that's if for some reason there was a blackout and your software didn't work and you had to get a report done. These days, you can do it in the software. But it's good to understand what's going on behind all of that. So once you do that, that's how we would come up with a z-score. In this case, the z-score is negative 2.6. So remember, the total area under the curve is 1. We've got a standardised curve now. We found out that 74 is equal to a z-score of negative 2.6. And we can look it up on the table. Negative 2.6, the probability of that is 0.0047. Okay, very small. It actually works out, the probability of not getting it, the opposite, is, hang on, am I reading that right? Oh, when you round it up, it's more than 90.9953, the chance of getting in the grey area there. So it's the same on the other side, except you'll see that when you go over this side, 2.6, 0.9953, because remember this table is giving you the probability of everything to the left of that z-score, okay? So if you go over to the other side, it's a 0.9953 chance that it will be everything to the left of that. But the red area is still the same probability. And so then if we wanted to say, well, what's the probability of coming on the inside of that? That's what we would call a two-tailed test. Before it was a one-tailed test. Sort of what's the probability of being on this side? In this situation, we're saying, what's the probability of being inside these, here we're saying, what's the probability of being inside or outside these two tails? So we would, what's the probability of being inside it, sorry. So multiply that by 2, come up with 0.0094, okay, which is a tiny, tiny amount. It's coming in at about 1%, okay. So you can see there the probability, when we talk about a confidence, hang on, I'm going to get to confidence intervals. But this relates to a 1% chance of if you draw a sample, they're going to fall in these little tails out the end there, okay, 1% chance. Okay, so instead of calculating frequencies and proportions for every data set, we can standardise, which is what we've done. We can provide probabilities of getting particular results, and that is the basis of inferential statistics, okay? You could work it all out, but what you will do when you're reading a p-value is you're looking at that probability there. That's a two-tailed significance, okay? So we'll be doing more of that in the pracs, and we've already done some in the prac last week or this week. So you've already seen the p-value. I'm going to run through a few more slides. I know that this stuff is a bit meaty, but I just want you to have, because we don't have lots of time in this course, I want to make sure that these foundations are lodged in there somewhere. So in terms of the p-value, we know that the p-value is the chance of obtaining an observed difference between a measured outcome and a null hypothesis. Okay, it's just what you were doing in the prac earlier this week. E.g., if chance is the only factor at play, there's a probability of 0.0047 that will get someone with 74 kilos or less from a population with a 100 kilo mean. Okay, that's what we were looking at before. And I hadn't told you the standard deviation was 20. So that's if chance is the only factor at play. Okay, remember we're drawing a sample from a broader population. Now, this is a bit confusing, but just to clarify the formal definition of the p-value, it's the probability of an observed data summary, in this case the average, the mean, the probability of the mean and its more extreme values given a specified mathematical model, okay? and a hypothesis, and usually we're looking at the null hypothesis. Okay, that's just a very wordy way of saying what we've been doing in the pracs this week, and you'll do more of it next week. What the p-value is not, so it's a probability. It's a probability between the mean and the sample that you get, but it's not a measure of certainty of results, and it's not an answer in and of itself. I'll explain that, and it makes sense as soon as you think about it. We always have to interpret that p-value in terms of the study that we're doing and the significance value that has been selected. And there should be a relationship between the significance value that you select and the actual question that you're dealing with. If it's incredibly important that there's no error, or that we don't make an error in deciding whether we accept or reject the null hypothesis, then we set that significant level lower. Okay, so 1%. In this course, we're usually working at 5%. In some types of social research, we might work at the 10% significance level. So you will see in some reports the alpha sign. Sometimes you also see CI for confidence interval, or sometimes SIG, as you saw in the SPSS output, and it's all talking about the p-value and the confidence interval of the p-value. And it's basically a measure of how much risk we're willing to take when we reject the null hypothesis. So this is the risk of rejecting the null hypothesis when we should accept it. Okay, let me explain that. So, alternative hypothesis says that there is a difference between A and B. The null says actually there's no difference. Okay, there's no difference between A and B. So when we're testing, we've done this already, declaring whether the null hypothesis, whether we accept or reject it. So for example, alternative hypothesis, eating 40 kilos of chocolate in a small amount of time will cause weight gain. Null hypothesis, eating 40 kilos of chocolate will not cause weight gain. It might be written like this. There's our alternative hypothesis, and there's our null hypothesis. So that all sounds good, but I want to test this because I like eating chocolate. And so I'm probably biased towards wanting to find the null hypothesis to be true. So we're going to, over 4 weeks, we're going to eat 10 kilos of chocolate a week. No problem finding volunteers for this study. We want to compare the original weight of people to their post-chocolate weight. Okay, so we're going to end up with 2 lots of data, 2 samples. And they're actually the same people, but measured twice. So we're going to talk about what that means a bit later on. It's a particular type of t-test, a paired t-test, because you've got the same people in each sample. And yeah, we'll talk about that in evaluation research. This is basically a pre-post test. We're measuring people before and after our test. Okay, pre-chocolate, the mean weight is 75 kilos with a standard deviation of 2.5 kilos. Post-chocolate, 80 kilos, still the same standard deviation. Okay. It looks like there's a difference, just visually, doesn't it? But you can see here that there's quite a bit of overlap. So that means that there could be a bit of chance in there that we need to actually measure it, how confident we are that it's because of eating chocolate that this has changed. Okay? There could be lots of other variables in play. Perhaps everyone, perhaps they were less active during that 4 weeks. So perhaps that was over the lead up to the exam period and the last couple of weeks of semester. I know I don't move very much during those weeks. So we have to do, just say we do our analysis and we get a p-value of 0.001. Okay? So that is going to mean if we have a 0.05 confidence interval, that we're going to reject our null hypothesis, okay? Even if we have a 1% confidence interval, the probability that we say it's not because of chocolate, sorry, I'm saying it the wrong way around. We're rejecting the null hypothesis, okay? So the probability that we have wrongly rejected that eating the chocolate makes no difference, is very low, 0.001. Is that making sense? If not, keep going over it. I'll explain to you later, okay? So if we set it at 0.05, it means we're willing to accept a 5% risk that we actually reject the null hypothesis when we should have accepted the null hypothesis, okay? If we set it at 0.001, the risk we're accepting of wrongly rejecting it is lower. It's 0.1%. No, it's 1%. No, it's 0.1%. Okay, I have to have more of my coffee. All right, so when we get a p-value and we compare it to our significance value to understand what that means, if the p-value is smaller than alpha, our significance level, then it means we've met our own requirement for statistical significance. So it doesn't mean that it's proven or definite. What it means is that the risk that we said as researchers that we're willing to take, we've met that level of risk, and we're going to say that we have enough evidence to reject the null hypothesis. Now, when I haven't had enough coffee, I do mix this up. But basically, there are two types of errors, type 1, type 2. You've probably seen this before. Type 1 is a false positive, where we reject the null hypothesis incorrectly, and type 2 is a false negative, where we accept the null hypothesis incorrectly. I'll explain what that means. And this is something nifty that I've recently found. So most of you will know the story of the boy who cried wolf. He said, there's a wolf, and there wasn't a wolf. And then eventually there was a wolf. He said, there's a wolf, and no one believed him. So the first time, when everyone believed there was a wolf and there wasn't, that was a type 1 error, okay? And then the next time, when they believed there was no wolf and there was a wolf, that was a type 2 error, okay? So as long as you substitute effect for wolf in that sentence, you won't confuse type 1 and type 2 errors. Bringing it back to the idea of a hypothesis and type 1 and type 2 errors. So remember what we're talking about here, reality, that's the broader population. The research, in this case, this is our sample, okay? And we want to know so here it's accurate. We do our research, we do our probability, we take the risk, and we say, no, we don't have enough evidence. We're going to keep the null hypothesis. And if that is actually matching the broader population, then that's what we want. It's accurate, okay? Alternatively, we do our calculations and we say, no, there's enough evidence to reject the null hypothesis. The alternative hypothesis is true. And if that measures reality, then it's accurate. Happy face. And so then type 1 and type 2 error, remember, this is a false positive. So just say we have set it at a 5% confidence interval. We do the calculation and we find out that it comes in at 4.9%, and we say we've met it, okay? We've met it. But there's still a chance, there's a 4.9% chance that there's something else is going on, okay? That we have selected that sample and that there's something other than chance going on, okay? That we've actually accidentally committed a type 1 error. So here, again, it's the opposite. It's the false negative. So just say we do our calculation on our sample and we say it's come in at 0.51, not enough evidence, okay, not enough evidence, and so it keeps the null hypothesis, but in reality there's still a chance that the alternative hypothesis is true, okay? I'll leave you to look over that, but that's basically, obviously we're trying to avoid this and this in our research, and that's the whole idea of setting appropriate confidence intervals and measuring those p-values. Okay, so that is, well, the first of the meatiest parts of the lecture. The next bit's not so meaty, but we're going to stop for a 5-minute break, and then we'll come back. By this clock here, it's 8:47. I can't really see what's up the back there. Well, let's start again in 5 minutes. Shake yourself off. Well done. You got through a big barrage of slides just then. Yeah. Yes, yeah. Yeah, yeah. The thing that we're wanting, the thing that we're hoping to find, it's not there. Yeah. And so we start with a conservative sort of approach that says, well, yeah, yeah. Okay, I think we're going again. Yes, green dot for audio. So this went up last night. I'm sure that you were all in bed early for getting ready for your 8 o'clock lecture. I've put another link there for people to post what they found most challenging. That can be anonymous. It's helpful for me to see what's important to go over or what extra information I can find to put online. For example, here I've got something on interpreting significance, just a one-pager, and then something, an overview of 2 sample t-tests. So when I know that something is a particular question, I'll find a bit of extra material and put it on there. Yep. So remember as well that because we've front-loaded this material, and you still have to remember some of it, enough of it by the exam, it's really good for me to hear what's been most difficult. You'll be able to jump back on that later in semester as well. But what I wanted to show you as we lead into this next part of the lecture is an example of evaluation research, okay? So when we're doing an evaluation of planning or management, there are different types of evaluations. Some of them are post hoc evaluations, often with environmental things or things that have occurred to us afterwards. We might have to do an experimental design, which is a post hoc only. Obviously, the strongest, most robust experiment that you can do is a strongly experimental design. Remember, we had different types of research in the first lecture, second lecture. If we have an experimental design, if we can have a pre and a post analysis. So we have a group of people, just say a group of people before something happens, the thing happens, and then we can analyse them afterwards, and then we can compare, and we can say something a lot stronger if we can do that. And so that's the basis of experimental design. I just wanted to give you this example. It's from a paper, it's fairly old now, 97, but it's looking at occupational health and safety, and it's what they call a meta-analysis. These people looked at a whole range of other evaluation studies that were done on the effects of OHS in the workplace. And so they looked at all different interventions and they were using that as their treatment. And they went through and they had a look and they were able to find a whole range of engineering interventions. So in OHS, you might, there might be a particular change that you make in terms of engineering the workplace. And you can see here that what they did was they had a look at what sort of design it was, pre-post, most of those. Pre and then post control, you'd have to look at that to see exactly what they mean there, and then how long they are as well. Okay, you can look at how the results were reported, etc. And so it's just an interesting overview. So in engineering interventions is one of the things with OHS where we actually change the equipment or the workplace, and then administrative interventions might be about new policy or new training, that sort of thing. I know you're not OHS students, but you'd be surprised how much it will be part of your working life. And so then they also looked at the design around administrative interventions. And so it's a good overview of this idea of evaluation research, that you can have different approaches, and they've got an interesting sort of argument in their abstract up here, and they're saying that when we look at all the studies here, the design, conduct and evaluation, we find that actually having that strict randomised controlled trials are rare, and quasi-experimental studies, so not randomised, you know, it's just the group that the researcher selects for a particular reason. And so setting up a quasi-experimental study, often use weak design, so don't go for very long, perhaps it's only post-hoc, not pre-post, etc. And so it's good overview of different types of evaluation. It's always difficult to get the especially in environmental issues, to have that baseline, because you never know what's going to happen in the environment. Similar with planning, there's a lot of unknowns. When we plan into the future, we don't know. So when they did the Brisbane City Plan before 2011, we didn't know that the whole city was going to flood, and so there was a range of things that had to change. But in terms of researchers, it might be very difficult to have the right data for pre to be able to do a pre-post. So it's something to keep in mind about having a strong business case in your work. So let's say a little bit more about evaluation research. So as I was saying, it's basically this idea that, hello audio. Okay. I'm hoping the audio is recording. There's a red dot there. Green dot, yes. Okay. We have a program and then we have observations. And what we're looking for is a program outcome relationship. This is the basis of a lot of research, which is, can we discover some sort of causal mechanism? So the program is what we do and the observation is what we see. And we want to know, is there a relationship between what we did and what we saw in our results? Okay, so if we're looking at definition, it's systematic assessment of the worth or merit of some object and the systematic acquisition and assessment of information to provide useful feedback. Okay. So there are different types, formative and summative. You might have come across this before, but this is how I think about it anyway. If you think about our experimental design from high control to low control, and we've already talked about different types of research. So we might have quantitative, there's different quantitative approaches from experimental design where we have very high control down to something that has very low control. In a few weeks, you're going to talk about qualitative science evaluations. So up this end, probably with higher control, you've got a qualitative survey where you're able to cut out a lot of confounding factors and just ask some people some very specific questions. And then as you get to low control, you might be doing a case study research where you're looking at a natural phenomenon and you actually can't put any controls around it at all. But when we're talking about evaluation, that's research, we're often looking at management as planners and managers, okay? So there might be often evaluations that happen of management, and so of the organisation, might be looking at its own activities. And then you might have other ones that are about the participants. So a business might look at the way they work internally, and then they might look at their customers as participant oriented. And there's an interesting overlap here that hopefully Christine will get time to talk about, which is called participant action research. And I just want to mention it briefly. In universities, it's not often given much time because as academics, we like to work over here. And this is seen as having low control, and it's more about participants rather than experts. And it's based on the idea that the participants actually understand something about what's going on for them. And as academics, we're always sceptical that anyone except us understands what's going on. But for particular types of problems, it's actually an incredibly brilliant design. And this is an interesting area of growth into the future, and something that we're looking at with the science policy interface. Instead of scientists doing everything over here and then handing it over to decision makers, if the participants in this situation might be planners and managers, and I was talking to someone in the NGO sector and they were saying we would love to be able to partner with universities and work with them so we can answer our questions better. Okay, so that would be an example of where you work with participants and they design the research and they're doing it, and it's often about them. Obviously, there's a lot of queries about what are the biases there and how do we can control them. Okay, but coming back to this idea of formative and summative evaluations, formative questions are aimed at improving the design or the performance. And so it often happens during a program, okay, or even before. So you might ask things like, well, where is the problem? How serious is it? How well is our program being delivered? That sort of thing. So it's formative, it's happening in the moment, and you can improve what's going on either in the near future or right now. Whereas summative is more focused on the outcome, okay? It's often after the fact. It's interesting, a lot of universities focused here on we're going to give you a summative evaluation of your courses at the end of semester, but it's actually useful for you to get that formative evaluation as you go along. And in the workplace, you want that formative evaluation as you go along. You don't want to just hear you're fired. That's the summative evaluation and you had no chance to change things. Okay. Those of you who worked with me last semester know the irony of me talking about that because I was a bit too busy to give good formative support. So these are the sorts of summative questions that you might, first of all, you have to ask, well, what sort of evaluation is feasible because it's after the fact. And so we often ask, well, what is the effectiveness of the program that has finished? What was or what is the net impact of the program? So it's about the outcomes, okay? So outcome evaluation, impact evaluation, cost-benefit analysis, etc., meta-analysis, they're all types of summative evaluation. We'll be looking at a few of those later in semester. Because it's incredibly important to be able to do, to talk about, when you talk about the outcomes of a particular planning intervention or a management regime, you want to know, or a development, what's the environmental impact of a development, you need to be able to do this sort of, well, what was the impact? what's the outcome of that particular program. So there's a bit of a structure. This is all pretty straightforward, so I can zip through this. Obviously we have a problem. Usually, in this sort of research, it might be a problem that stakeholders have recognised, or your managers, or whoever. Then in this situation, your hypothesis is your research question is what you think is going on. Then we've already talked about the need to operationalise the construct. So what is the cause? What do we think is going on here? And then we have the population, we take a sample. And we obviously have the outcomes, the effects, and we need to measure those. There's always questions about the design, and it's often based on, well, who is this program for? Is this a result for researchers to write in a journal? Is this for managers to better manage their organisation? Is it for participants who have to interact with that program but they don't get to manage it? And it's important to note where evaluation fits. Most of you would have seen a program cycle or a planning cycle, policy cycle before. And so if we say the planning cycle, the planning phase, we identify, or so we formulate a problem, issue or concern, conceptualise how we're going to tackle that, then we detail that, we detail the different alternatives, evaluate which one's best, and put into action. And then on a standard policy cycle, then we put into action, and then we measure the outcomes and we evaluate it and we go around again. So that entire evaluation phase is usually just 1 or 2 steps on a planning cycle. But there's actually a whole sort of mirror that happens there. So it's another flick through that cycle, but it's based on evaluation. So you have to formulate your evaluation questions and hypothesis, think about how to measure that, think about different ways to design it, and then select a design, put the design into action, analyse it, and then actually use the results. You'll be surprised how often an evaluation happens and the results don't get put into action. So that is research, okay? A lot of people going through uni say, well, I'm just going to go out into the workforce, I don't want to be a researcher. But whenever you're trying to find out what's going on in a systematic sort of way, or what has happened, you're doing research. And this is a very practical way to think about the work of planners and managers and what's going on. If you want to be a good professional, you might have to do some of that informally. You won't always have the resources to look at your own work and evaluate what's happened. But I encourage you to try and at least do that informally for yourself. Keep good notes, write down what happened when you tried different things, what happened from particular programs you were involved with, and you'll be able to refer back to that. Because workplaces often don't have the funding to do this in a really detailed way. Okay, so the basic evaluation model, this might be, and maybe going back to that chocolate thing again, we might have a group that eats 40 kilos of chocolate. We might have a super group that does 80 kilos of chocolate. That would not be good. And then we might have a control group that does down here I've got no program. The control group. Here we might have, perhaps more with medicine than chocolate, you might give people something that they think is the treatment, but it's not. So see if there's some sort of placebo effect. And then you're able to correlate those different groups with different outcomes and use that with your pre and post analysis, your evaluation of whatever's going on. Okay, so we'll look more at evaluation research as we go along. And the prac today, as I said, the prac next week, is based on an evaluation research that was done with different treatments. So different urban moose populations and their exposure to stress. They were trying, their exposure to urban settings, and they were trying to see if stress, if there were different levels of stress in the moose in the national park compared to different urban settings. Okay, so then once we've done that, just say we've set up our evaluation, we've got our different samples from our different levels of testing in the program, and then we want to test if those differences are actually significant. So that's what this next part's about. So when we're testing for the differences between groups, we also need to distinguish between statistical versus practical significance. Okay, I'll explain more about that in the prac. So you've already seen a non-parametric test of testing is there significance between two different groups, and remember non-parametric is assuming that the data is not normally distributed. It's a less powerful test. We're actually just ranking. It's sort of ordinal. It's not interval or ratio data, but that's what we did, and that's what you're doing in the prac this week. And then we have a parametric test, and in the prac this week I got you to compare the Mann-Whitney and the independent t-test, which is parametric, and this says lab today, it should say next week. The parametric test really, it's meant to be done when the data is normally distributed. That's the assumption that's going on. Okay, I mentioned before that when we have a paired t-test, we have the same subjects pre and post. So there's different types of t-tests. I'll put some extra info in the lecture folder for next week on that. And then also next week we'll look at ANOVA, which is a different sort of test where we might be comparing between two or more groups. T-test, we're just talking about two groups, okay? So, independent t-test. We're checking whether the mean between two groups are statistically different from each other, okay? So we had our chocolate example before, and we wanted to test the differences between pre and post, so it was a paired test. Is that statistically significant? So therefore, the null hypothesis is that there's no difference. So the mean of one of our groups is equal to the mean of our second group. That's our null hypothesis, okay? No difference between the population means or the sample means of the two groups. Okay, so this might be our two groups, and we're asking, is there a statistical difference between the mean for the same variable? So we might have a control group mean, they're the people that didn't eat the chocolate, and then we might have a treatment group mean, the people that did eat the chocolate. And we're saying, is there a difference? Okay, but we need to think about, well, what does difference, and here's the English word, what does difference mean? What's the meaning of the word difference? We can explain it in different ways. Okay, so what does difference mean? We could have medium variability, we could have high variability, a much larger spread, we could have a low variability. Now each of those has the same distance between the mean of our treatment group and our control group. See that? The same difference, but we've got a wider spread. So which one do you think shows the greatest difference? Does anyone want to take a guess? Which one is most different? Okay, you're whispering to each other, which is fantastic, peer-to-peer learning. Basically, this one's mostly the same, isn't it? Because there's a huge overlap. This one's got moderate overlap. This one's got the least amount of overlap. So that you would say that these ones are most different. But what a t-test does is it's a function of the mean relative to the variability. Okay, we need to think about that variability, not just the mean, or else we could end up like there, coming up with the same score when obviously those groups there's difference between them. So the way a t-test does it is it's a bit like if you were trying to talk to someone in the lecture theatre and everyone was quietly talking to each other. Everyone talking to each other is like the variability. It's like the noise that's going on. And you two trying to talk to each other, sending a signal across, that's like, that's the signal. That's like the mean, the variable that we're measuring. And so I'm getting to what this means. When we're doing a t-test, we're basically dividing the signal by the noise, okay? The signal being the difference between the two group means, and the noise being the variability between the groups, okay? So in that case there, we had the same difference between the groups, but we had low variability. So if you think about this, it's like a fraction. What happens as we lower the variability of a fraction, or lower the denominator of a fraction, that number is going to get larger, okay? So the t statistic will get larger as we lower the variability. If you had to do it by first principles, that's what you would do. You don't have to for this course, but I will put a bit more info about that for people that are interested. Basically, in this course, you have to know how to measure what's going on in your output from SPSS, and this is what you'll be looking at in the prac next week. So you can see there that you've got, so this is the actual data set you'll be looking at. There are two different samples of moose poo, and they're looking at the level of the stress hormone, in one from Denali and one from Petersville. Okay, you can see there's a difference there. The mean between those groups is 51.5 for Denali and 58.18, so 58.2 for Petersville. Okay, in the t-test, there's two steps for interpreting it, especially in SPSS. First of all, there's this thing that's called the Levene's test for equality of variances, okay? And so you need to look at that, the p-value of the Levene's test will tell you which line to read in this table, okay? It's quite easy when you think about it, okay? So if the Levene's test is, if you have a significant result for that, so if it's significant, we reject the null hypothesis. The null hypothesis for the Levene's test is that there's equal variances, so the alternative hypothesis is that there's not equal variances, okay? And then that'll tell you which p-value to read, okay? In this situation, they're the same, but sometimes they're not. Okay, so that will all make a lot more sense once you actually do it, but where basically you've got two groups, you've got two different treatments, you've got two different group means, the results, and you're trying to say, you're trying to work out what's the likelihood that the difference between the means is due to our treatment. Okay, so this last part of the lecture we're going to talk about bivariate correlations. This is another thing that's in the prac. Again, they like to have big words for things. Bi meaning two variables, and correlation, do they have some sort of, do they move in similar ways? Okay. Now, correlation doesn't equal causation. I won't play this. There's a really crazy statistician that talks at 100 miles an hour. It's quite amusing. Go to that link and have a look. And he's talking about the difference between correlation and causation. So basically, correlation is not equal to causation. All we're saying is do these variables seem to move in the same way? Or how do they move in relationship to each other? We don't know whether there's a causal mechanism making that happen. So for example, and this is a hotly debated one, does the consumption of meat affect the levels of cancer in a population. So this is from a study, and you can see here that the more meat that you consume in grams, and this is done with women. I don't know what the exact scale is there, but the incidence of colon cancer per 100,000 women. Okay, and you can see there, what would we call that sort of, what would you say? Is there a relationship there? How would you sort of describe that, if you have a think about it? It kind of looks like there's something going on, doesn't it? There's a general trend there that as we increase the daily consumption of meat, it seems like there's an increase in the colon cancer levels. It's kind of interesting when you see, the wealthier countries up here. But then, remember, it doesn't mean that there's a causation, just that there seems to be some sort of positive relationship going on. There could be lots of other things going on there. What could be a confounding variable in this situation?
Lifestyle.
Yep. Yeah, exactly. So that's just looking. The other thing is you could say, well, maybe that's skewed by gender. We don't know. They've just looked at women, and they've just looked at colon cancer. Well, here's another one that looks at the incidence of breast cancer. By the way, I eat meat. The person that first showed me these slides is a vegan. So again, we can see some sort of relationship. It's hard to tell, isn't it? You can see the dots all over the place. Interestingly, when they looked at trends in some of these countries, that some of them, the incidences were going up, even though the consumption of meat was going down. And there was a couple of them here where the incidents were going down, even though the consumption of meat was going up. So they were saying it's a correlation, but it's really complicated about what's going on. Yes. Yes, but before you do, I just have to remind all of you that if you say something in the audience and I don't reflect it back into the recording, I'm trying to remember to do that. I've had some feedback from externals that sometimes I forget and they want to know what you're saying. Yeah.
It's just that they did a similar study with cancer and arthritis and chili consumption.
Yeah.
And they found that more chili means that you have less arthritis. So it's pretty vague, but it's just, it's correlated, but vague.
Yeah, okay. So there might be something going on?
Well, Indians tend to have less arthritis and cancer than they used to when they eat a lot more chili. So I don't know whether that amounts to anything.
Excellent. Well, I'm going out to get a nice hot curry for lunch then after this. But, you can see how these sort of studies can be used to kick off the next health fad. But I guess the question is, what sort of correlation, how strong is that correlation? And so up here we have the R value, which is a measure of correlation, and it's 0.827. Now, if I was to tell you that the correlation, the R value goes from -1 to +1, do you think that that is a strong, medium, or weak correlation? Strong, yeah. So I've mentioning before that in general, when we've got a scale 0 to 1, you can say that 0 to 0.3 is weak, 0.3 to 0.7 is sort of medium, 0.7 plus, we usually call that fairly strong. Again, it goes from negative to positive. Does anyone know why? This is positive because as one increases, the other one increases. If that was negative, we would expect to see that whole thing running back the other way. So as the y-axis decreased, the x-axis would increase. So you'll be looking at some of those R values in the prac next week. That's what that's talking about. So what is involved in that is what we call a regression. And so that's a regression line through the middle. If everything was along that line, the R value would be 1. Again, that's another meat consumption by cancer in general. This time Mongolia is way up the top there. So, yeah, the jury's still out on that, but there seems to be more and more evidence gathering that there is some sort of relationship. Those of you working in real-world complex systems, we often start with research like this because there's so many variables in play. The first thing we have to do is just sort of say, how are these variables moving in relationship to each other? And then you start to get specific experiments that might be able to isolate certain variables and test them. These are very difficult to test though. There's another one. But again, as we were saying, there could be a whole range of things around lifestyle, around how sedentary you are. And again, you can see that if you look at one other variable, body mass index, there is also some sort of relationship there between a body mass index and the country that you're in. And they correlate more or less with some of those examples there. Okay, well, we might actually finish early today. So, covariance and correlation. Okay, covariance is a measure of how one variable co-varies with another variable, whereas correlation is when we've standardised it. Okay, and so because it's standardised, we can then compare it with other things that are going on. So if you had to do it from first principles, where n is the number of data points, so n minus 1, for those of you who know about degrees of freedom, that's basically what degrees of freedom is, n minus 1, where you have one variable, which is x, and a dependent variable, which is y, and then the one with the bar over the top is the mean of x, and then obviously that's the mean of y up there. So you could work out the covariance there, and then the way that they standardise it is by dividing by the standard deviation. Okay, so standard deviation of variable x, standard deviation of variable y, and you would get that. I'm not trusting this system now after last week. Another thing that you will do in the test, in the prac, is sort of the step before when we're looking at correlations. So here's two variables, and you'll generate a scatter plot. So this is an experiment out of one of your readings textbook, and that's how you do it in SPSS at the top. And this was an experiment where they measured the responses between, first of all, they showed people a picture of a spider, and they measured their stress levels, their change in stress, and then they showed them a real spider. They were trying to work out, there's sort of experiments into phobias. I can see some negative body language. People that even talking about spiders, maybe your stress is going up. So they measured that. There's a nice example of a spider. So they showed them a picture, measured their stress level, then showed them a real spider, and they wanted to see, is there some sort of relationship? The hypothesis was that there is. It sounds kind of logical, and that's the results that they got. And then if you were to do a regression line through that, you could then work out how strong that relationship is in that situation. You'll be looking at it in terms of some other variables with that related to that moose experiment. So this is the R value that we had up there before, the Pearson's product moment. People just talk about the R value, really. And it's important to note that it assumes a normal distribution, okay? It ranges from -1 to +1, as I said before, and it's used with interval or ratio data. It generates a p-value to test whether the relationship between the two variables is significant, okay? So you go into analyse and correlate, and you'll be able to find the Pearson's product moment or Spearman's row. I'll talk about that one in just a second. You'll come up with a table like that when you do that analysis, And so you can see here, it's quite a small sample size. N equals 12, only 12 people in this experiment. But the Pearson's, the significance was 0.067, okay? So there's your R value, 0.545. So what sort of strength relationship is that? About medium, okay? It's in the middle there, between 0.3, 0.7. And the p-value is 0.067. So remember we were measuring if there is, did I have the hypothesis on there? Test whether the relationship between two variables is significant. So the null hypothesis is that it's not significant. The alternative hypothesis is that it is significant, the relationship. And so here at the 0.05, at 5% confidence interval, we would reject the null hypothesis, okay? And we would say, we would accept the null hypothesis. And we would say that there isn't a relationship there. We don't have enough evidence. We don't have enough evidence to reject the null hypothesis. Okay, Spearman's row, again, remember I was saying there's a lot of tests in stats that are quite similar. It's similar, but it's treating the data as if it's not normally distributed. So it basically ranks the data, and so it's not as powerful a statistical test. So if you were to do it there with the Spearman's row, you can see that there's 12. You can see that the R value up here is 0.49, and you can see here that the p-value is 0.1, okay? So as I was saying, it's not as powerful. So if I go back to that one, significance 0.06, okay, it's a lower p-value. In this one, it's a higher p-value, okay? So it's good to start to understand the pattern between when we talk about when a test is more powerful, it's about its ability to discriminate in terms of that risk of rejecting or accepting the null hypothesis incorrectly. Okay. So the last thing is the coefficient of determination. And this is it's made by squaring the R value. It measures the amount of variance in one variable that is explained by the other variable, okay? The amount of variance in the dependent variable explained by the independent variable, the one that we can change in our treatments. As I said, found by squaring the R value. So if R is 0.545, then R squared is 0.297, and the way we would interpret that is to say that 29.7% of the variation in Y, our dependent variable, is explained by the variation in X, our independent variable, okay? When you're writing this up in your pracs, I want you to follow this formula of declarative finding followed by statistical evidence. So in this situation, there's an R value of 0.58, comma, p-value of less than 0.05, okay? So you've said it in words. There's significant positive correlation between age and length of residence in Alaska. That's the correlation. And that's the p-value for that correlation, okay? Report the value of the statistic and then show whether the p-value is less than or greater than the cutoff for the significance. Okay, I just want to finish the statistics stuff with this slide. This is what you'll be doing in the prac, and it's a partial correlation, okay? So here's an example of partial correlation where you want to work out whether the relationship between exam performance, exam anxiety, and revision time. Okay? The way you would do this is you would you look at two variables at a time, so you're keeping the other one constant. So you'd say the variance accounted for by exam anxiety is 19.4%. That's the variance of exam performance by exam anxiety. The second one, you would then hold the other independent variable, you would hold the other one constant. So you hold that exam anxiety constant, you look at revision time, and you would look at the variance, and the variance here is 15.7%, and then this is what we'll show you in the pracs. You then do a correlation between those two to find out what is the unique variance of each and the relationship between those. Okay, I just want to introduce that. In the prac, we'll walk you through it, and then you'll see that it's actually fairly straightforward when you follow the steps. Okay, now before you go, I do want to show you a little bit about this study so that you have some good grounding in this. So you'll be looking at a data set that is different to the first two pracs. As I said before, you're looking at you're going to be looking at a study on moose. Here we go. So I've got a little overview here for those of you who want to go back over it. But basically, it was done by a grad student in Alaska, and they were wanting to look at stress responses to snowmobiles in moose. Okay. There's moose. Actually, I've seen a white moose on the news at the moment. Everyone's going crazy about it. There are some albino ones. In this particular city, there are moose. It's very, very high usage of snowmobiles, and that kind of correlates with urban areas. There are moose that actually go right into the city. So the purpose of the study was to gather baseline information about the levels of stress and evaluate the potential contributions of recreational snowmobile use to those stress levels. So the process that the researcher went through was to measure and compare the stress levels in areas with snowmobile use and without snowmobile use. So these are the different treatments in this study. And then compare the stress levels. And then the next step, there were two steps, was then to also compare these stress levels with the stress levels of urban moose. Okay, so there were two hypotheses. The moose in an area with snowmobile use have higher stress levels than moose in an area without snowmobile use. Sounds pretty logical. And the moose in urban areas have higher stress levels than moose in rural areas. So stress, I guess this is an interesting example because then, you're going down into the biology of what's going on. So here you can see the moose right up in amongst urban development in the city, and we want to know what sort of coping response is happening as a result of living in that environment. So there's a whole range of things that could be affecting stress. It could be to do with food availability and quality, could be to do with predation, reproductive status, temperature, etc. And they were especially interested in this because there was a rapid increase of snowmobile use happening, but you also had an economy that was really dependent on these natural resources. So tourism was important, but having the moose there for tourists to look at was also important. But it was also new areas. They were considering, should we open up new areas for snowmobile use? So the researcher went through a bit of a process to work out, well, what is the stress response? So this is an example of putting together of operationalising the concept of stress in moose. And so it was operationalised by looking at these stress hormones, and maybe we can measure these stress hormones as a construct for stress, or operationalised of stress, sorry. They decided on fecal measurement because it was non-invasive. It gave sort of general measures. So if you think about it, if we were to take a blood test, that would also affect it as soon as you're being invasive. But also, if you don't know if a snowmobile has just gone past the moose or not. So you need a more general measure of stress over time to understand. And of course, it's practical. Has anyone seen a moose in the wild? I haven't. But they're pretty big animals and they're actually pretty dangerous, and so you need a practical way of doing it, not having a couple of 100-kilo beast running after you. So here's Anchorage, which is the city we're talking about in Alaska, and one of those samples is Denali, so the moose are out in the national park there. There's snowmobile use. There's no snowmobile use out here, but there is here. So collected from all these sample sites. So Denali was made up of all these sample sites, and then Petersville is made up of these sample sites along the creek here. There they are, having fun collecting samples. Collecting poo is fun. So it goes through a bit of the method. You can look at that if you like. There's a picture of the researcher. And then this is the second hypothesis where they're looking at the stress levels in urban moose. So you'll see that there are 3 samples here related to different treatments of urban exposure, I guess. So out here in the hills, you've got your larger houses, the population isn't so high, there's not so many vehicles driving around. Then you've got purely sort of urban setting here in Midtown, and then over here I think that's the airport just there. So you've got urban but also exposed to pretty high levels of noise. So they're the samples that you'll be looking at. This is how they prepared those samples and then analysed them, for those of you who get really into this sort of thing. And then in analysing them, and they looked at those stress hormone levels, you could see that they did find that the ones with the snowmobile use had higher stress levels than the ones in the national park, and that the urban moose had higher levels than the non-urban moose. But then the calculations that you're going to do go into a little bit more detail about, so there is a difference, but what does that difference mean? How significant is that difference? And that's going to be really important. If you think about the practical application of this, which is going to be planning for tourism, it might be thinking about urban planning, urban form into the future. It's talking about natural resource that tourism is dependent on. You want to have a good business case for what you're proposing here. Whatever you propose is going to upset some people, okay? Planners, you're probably getting used to the idea that good planning often upsets at least some people, and environmental managers, hopefully you're getting used to the idea that you need to get the strongest business case possible so that the people that control the money, which is usually not the environmental managers, that you get their attention around the strength of your case that you're putting forward. Okay, so this is why you're going to be testing that, because although there's a difference in the means, you can also see that there's varying variability. There's different variability between all of those samples. And so you sort of go, well, is that a significant difference between 1 and 2? Is that a significant difference between the urban moose in 3, 4 and 5? And that's what you're going to be calculating with the t-tests and with the correlations. Okay, just check if there's anything else that I should say. Well, they were the end recommendations that came out of the test anyway. I'll leave you to have a look at that. but you can see that it was used in a very practical way to talk about where they would guide snowmobile activity, at what time of year. So in winter, perhaps they were going to especially target it. Obviously, in winter is peak snowmobile use, and then they were going to have particular instruments or tools or policies that they were going to put in place to respond. So I like this example because it gets you to do some practical stats on something that actually had policy outcomes, and in a couple of years you might be thinking about probably different problems, but problems with similar dynamics. Okay, so we'll finish it up for there today. One last thing to say about my consultation. I'll be slightly shifting the time from 10:30 instead of 11 till 1, 10:30 till 12:30 for the rest of semester. I'll put an announcement on Blackboard about that as well. Okay, thank you for your time, and I'll see you in the practice.